The Cajon Hypothesis. That which withholds Eschaton, the Cajon Hypothesis for resolving the Fermi paradox. Anatoly Karlin. October 20, 2019. Narrated by Skeptical Waves. I have been mulling over the ideas in this article since early 2016, when they crystallized in more or less their current form. I am not quite sure whether these ideas are rather important, or the ravings of a lunatic. But I am certainly glad to be able to finally unload them from the confines of my mind, so that they can now torment people much brighter than myself, and, hopefully, provoke them into making further progress on what appears to be a very much unexplored area of potential existential risks. I am grateful to Michael Johnson, Qualia Research Institute, for multiple very helpful and productive discussions, suggestions, and help with editing. Thanks also in order to many members of the East Bay Futurists for entertaining my initial rants about aliens and simulations. Abstract. A corollary of the simulation argument is that the universe's computational capacity may be limited. Consequently, advanced alien civilizations may have incentives to avoid space colonization to avoid taking up too much calculating space and forcing a simulation shutdown. A possible solution to the Fermi paradox is that analogous considerations may drive them to avoid broadcasting their presence to the cosmos, and to attempt to destroy or permanently cripple emerging civilizations on site. This game theoretical equilibrium could be interpreted as the Cajon, that which withholds Eschaton, doom, oblivion, the end of the world. The resulting state of mutually assured xenocide would result in a dark, seemingly empty universe intermittently populated by small, isolationist hermit civilizations. Introduction. In October 2017, a strange object appeared in the skies. Oumuamua, or Scout in Hawaiian, was the first confirmed interstellar object to pass through our solar system. As Robin Hanson pointed out, it was suspiciously extreme in many ways, highly elongated, with a very fast rotation speed, no outgassing as with comets, and a strongly red color typical of metallic asteroids. Could it actually have been a scout in the most literal sense of the word? The suggestions that it might be an alien spaceship did not just come from hyperactive sci-fi aficionados. The recent discovery of the more typical 2I/Borisov suggests that interstellar visitors are far more common than previously thought. Nonetheless, this doesn't contradict the possibility that one fine day in the coming century, one such scout from outer space will do in our civilization and our species, with no warning and for no apparent reason, with due apologies to Neil Stephenson. As I will argue in this article, this reason may well be not only perfectly logical, but born out of existential necessity. Filtering the Great Filter. The most merciful thing in the world, I think, is the inability of the human mind to correlate all its contents. We live on a placid island of ignorance in the midst of black seas of infinity, and it was not meant that we should voyage far. The sciences, each straining in its own direction, have hitherto harmed us little, but someday the piecing together of dissociated knowledge will open up such terrifying vistas of reality, and of our frightful position therein, that we shall either go mad from the revelation or flee from the deadly light into the peace and safety of a new dark age. H. P. Lovecraft. Robin Hanson's answer to the Fermi paradox, where is everyone? Is that the apparent rarity of advanced alien civilizations is due to some bottleneck event that all intelligent life has to go through. One may view this concept as an extension of the Drake equation, under the additional assumption that some of its values are so low that the average galaxy isn't likely to host much more than one civilization that emits detectable signals into space at any particular point in time. It is possible that the great filter lies in our past, meaning that we are safe, and a ball of hedonium may soon envelope our planet and suffuse our future light cone. In a recent paper, a team of futurists recalculated the Drake equation, instead of using point estimates, which typically yield an infinitesimal probability of our galaxy containing no alien civilizations. They calculated the distribution of expert probability estimates, ran a Monte Carlo simulation, and deduced that there is a 1 in 3 chance that we are alone in our galaxy, effectively dissolving the Fermi paradox. We should hope that they are correct, since the alternative possibility, that the great filter lies in our future, very likely dooms us to imminent extinction. Shadows of the past. If the great filter lies in our past, then it would imply that at least one of the former is very rare or improbable. The evolution of life. Certain evolutionary milestones. The evolution of intelligence. Advanced technological civilization. The evolution of life. Straddling the warm Goldilocks zone between the sun and the cold emptiness of outer space, perhaps Earth was uniquely optimal for the emergence of life. This rare Earth hypothesis has been challenged in recent years by the discovery of vast numbers of Earth-like planets. However, perhaps a weak version of Ray might still hold, that Earth is optimal for the fast emergence of complex, intelligent life. For instance, at least two critical evolutionary leaps, the appearance of eukaryotes and of large metazoans, may have depended on large, creative destructive oxygenation events. If the Earth's oxygen absorption capacity had been higher, complex life might not have had time to emerge by the time the Sun fried our planet in another billion years. Evolutionary milestones. Life appeared, in geological terms, almost immediately after the formation of Earth. So abiogenesis is unlikely to have been the principal barrier. Following the evolution of the first self-replicating molecules, there was 1.8 billion years of near biological stasis. Perhaps the likeliest candidate for the Great Filter was the transition from prokaryotes to eukaryotes, which were a prerequisite for the appearance of complex, multicellular organisms and sexual reproduction, both of which may have also been improbable. Conversely, transitions that evolved independently on many separate occasions, limbs, sight, photosynthesis, may be safely ruled out. The evolution of intelligence. Nervous systems with distinct neural signaling molecules, the building blocks of big brains and intelligence, evolved independently across both ctenophores and Kundarians/bilaterians 500 million years ago. Moreover, according to the Red Queen hypothesis, organisms don't exist in a vacuum, but need to compete against other organisms within a mutable environment. Since you can't stand still indefinitely, this should drive the evolution of more complex life forms. This theory is backed by evolutionary history. Since the Cambrian explosion 550 million years ago, the maximum encephalization rate has been constantly doubling every 50 million years. More broadly, there has been exponential growth in minimum genome size since the dawn of life. As Pierre Teilhard de Chardin and Vladimir Vernadsky had intuited in the 1920s, evolution is creative, with an overarching teleological drive towards greater complexity and intelligence. Nor is there good reason to believe that there is anything particularly unique or improbable about human intelligence. The world after the dinosaurs has seen convergent evolution of greater intelligence across the entire swathe of the world's habitats and animal taxa, dolphins, whales, and octopuses in the oceans, corvids and gray African parrots in the skies, and the great apes, elephants, and some monkey species on land. If humans were to disappear off the face of the planet today, there will be plenty of candidate species to rekindle civilization. For our own part, hominins only split off from primates 15 million years ago, and our brains have been exploding in size and capability ever since. Even the theory that there was a discrete great leap forward in human behavioral modernity 50,000 years ago has been sidelined in favor of explanations stressing continuous and accelerating change. Advanced technological civilization. Technological growth has been increasing at an exponential rate with remarkable consistency for mankind's entire history. Agriculture began 10,000 years ago. The Industrial Revolution took off around 1780. In the past couple of decades, the new science of cliodynamics has provided a strong theoretical basis for this pattern. The basic idea is that as population rises, you get more potential inventors, who create more technology and increase the carrying capacity of the land, resulting in higher populations, more potential inventors, etc. Although this basic mechanism is punctuated by Malthusian cycles, a euphemism for population collapses in the wake of disasters such as droughts, famines, plagues, civil wars, and nomad invasions, the exponential trend was remarkably stable in the long run. Other positive feedback loops include literacy and technologies to create more technologies, such as paper, reading glasses, the printing press, and computers. Human accomplishment, as proxied by the per capita incidence of great scientists and artists, also rises exponentially over the past 2,500 years, peaking in the late 19th century. The history of science and technology is also replete with examples of convergent evolution. Fire was invented, forgotten, and reinvented by countless numbers of disparate human bands. Both agriculture and literacy were independently discovered across multiple locations. The ancient Greeks almost got to the steam engine, and there were proto-industrial revolutions in the Roman Empire and Song China before the real deal got going in late 19th century Britain. At that point, the scientific revolution had been ongoing for more than 2 centuries, and more than half the denizens of the European core were literate. At that point, even if Britain had been swallowed up by the sea, an industrial revolution in that region of the world had long since become inevitable. Gloomy presentiments. Future great filters are mostly coterminous with the concept of existential risks and determine the value of the final term in the Drake equation, which refers to the length of time over which advanced civilizations release detectable signals. In a seminal paper, Nick Bostrom defined X risks thus: one where an adverse outcome would either annihilate Earth-originating intelligent life or permanently and drastically curtail its potential. He also pointed out that a very strong indication that the Great Filter lies in our future would be the discovery of evidence of past life, especially complex life, on Mars, or elsewhere in the solar system. At a single stroke, this would rule out the earliest and some of the strongest candidates for the Great Filter at a single stroke, and would constitute by far the worst news ever printed on a newspaper cover. Major candidates for future Great Filters can be divided into three major bins. Geoplanetary, for example asteroid impacts, gamma-ray bursts, GRBs, geomagnetic reversals, supervolcano eruptions, megatsunamis. Technogenic, for example nuclear warfare, anthropogenic climate change, pollution, resource depletion, dysgenic decline, bioweapons, nanotech, malevolent agi. Theoretical, for example superpredator civilizations, our simulation shuts down. Geoplanetary X risks. These are characterized by being either eminently survivable, at least on a civilizational scale, or highly unlikely even on Terran timescales. One study found that there's a less than 1% chance that our galaxy will produce a GRB anytime in the future, let alone one pointed at the Earth in the near future. If our hunter-gatherer ancestors survived the Toba eruption 72,000 years ago, then modern civilization will surely survive another Yellowstone eruption. An asteroid impact on the level of the KT extinction event, which did in the dinosaurs, is only expected to happen once every 100 million years. No dangerously large asteroids have been observed on a collision course with Earth, and even if they were, well, if early mammals survived KT, then so will humans in deep bunkers and nuclear submarines. All of these scenarios will be extremely disruptive, causing dozens if not thousands of megadeaths. But in almost all these scenarios, some humans will survive, and they will be able to rebuild industrial civilization. It can't be completely excluded that a really large asteroid, greater than 100 kilometers in diameter, a GRB burst, or something more exotic hits us. However, it would be extremely strange, not to mention extremely suspicious, if a geoplanetary Götterdämmerung was to do us in just 100 to 200 years after the invention of radio, during a time when we might be at the cusp of a technological singularity. Then again, we wouldn't have long to speculate about the cosmic injustice of this. Which may well be the main point. Technogenic X risks. This consists of classic 20th century concerns, nuclear war, dysgenics, and resource depletion, today's hot topic of man-made climate change, and futurist concerns such as GNR, genetics/nanotech/robotics, technologies and machine superintelligence. The megatonnage of the world's nuclear stockpiles are an order of magnitude lower today than during the height of the Cold War, not to mention 6 orders of magnitude lower than the energy released during the Chicxulub impact that did in the dinosaurs. Even so, many serious assessments even during the Cold War projected that a solid majority of the American population would survive a full nuclear exchange with the USSR. Tens of millions would die, and the bulk of the capital stock in the warring nations would be destroyed, but as Herman Kahn might have said, this is his parody in the movie Dr. Strangelove said, this would a regrettable but nevertheless distinguishable outcome compared to a true existential risk. In the long term, radioactivity will dissipate, the population will recover, and infrastructure will be rebuilt. In the past decade, climate activism has aroused the same intensity of passion as concerns over nuclear war in an earlier age. But we need to keep things in perspective. The IPCC does not project global warming much greater than 5.0 degrees Celsius by 2100, even under the most pessimistic emission scenarios. There is also a case to be made that moderate global warming may be a net good in terms of crop yields due to greater precipitation and carbon fertilization. However, even the most extreme projections such as the clathrate gun going off and zones of uninhabitability spreading across the mid-latitudes are unlikely to translate into James Lovelock's apocalyptic visions of breeding pairs desperately eking out a hardscrabble survival in the Arctic. The Arctic was a lush rainforest when global temperatures were at such elevated levels, and will be able to support advanced civilization. More importantly, there just isn't enough sequestered carbon to lead to a runaway greenhouse effect that turns our planet into Venus, at least under current levels of solar radiation. A relocation of the locus of human civilization towards the far north is not an existential risk. Similar considerations apply to pollution and resource depletion, confusing degradation and difficult adjustments with existential risks. First, it is not clear that things are actually getting worse. Environmental standards have been soaring in the developed world. For example, the Thames is now cleaner than it was in the 16th century, and new technologies are constantly opening up access to previously inaccessible resources, for example hydraulic fracking. Second, while future energy shocks may still impinge on living standards, there are no grounds to think they will cause long-term economic decline, let alone technological regression back to Stone Age conditions as some of the most alarmist doomers have claimed. There are still centuries worth of coal and natural gas reserves left on the planet. Nuclear and solar power have only been exploited to a small fraction of their potential, and hydropower, which has some of the highest energy returns on energy invested, isn't going anywhere. Furthermore, we still have a lot of potential fat to cut. Low car ownership and the extinction of budget airlines do not preclude continued radio emissions or rocketry. For example, see the USSR. Much of the developed world has experienced dysgenic reproduction patterns, duller people having more surviving children than brighter people, for over a century. Although this was long masked by IQ gains from better schooling and nutrition, that process seems to be coming to an end. Meanwhile, the problems that need to be solved for scientific and technological progress to continue are getting harder, not easier. Since almost all scientific discoveries accrue to a small cognitive elite in the world's rich, high IQ nations, this suggests that technological progress may slow to a crawl during this century as the world's remaining smart fractions get depleted, assuming that there are no abrupt discontinuities in humanity's capacity for collective problem solving, such as genetic IQ augmentation or machine superintelligence. But will this idiocracy be permanent? I doubt it. Since fertility preferences are heritable and ultra-competitive in a post-Malthusian world, we can expect an eventual reversal of the demographic transition. This renewed expansion will last until the world hits the carrying capacity of the late industrial economy, ushering in the return of Malthusianism and reasserting the eugenic fertility patterns of the pre-industrial world. Consequently, dysgenic decline does not constitute an existential risk. However, it may have the effect of extending the period of time that future humanity will be subject to increased levels of other existential risks. The final major source of technogenic existential risks concerns new technologies, in particular, genetics, nanotechnology, and robotics, GNR. In an ideal world, they promise us a utopian future of radically expanded lifespans and abundant material wealth, if not the secular equivalent of transcendence. But GNR technologies may also be the instruments of our demise. Since bioengineering doesn't require an extensive industrial infrastructure, like a nuclear weapons complex, the means to inflict massive damage may be democratized, vastly increasing the probability of devastating pandemics unleashed through bioerror or bioterror. The engineer Eric Drexler has suggested that nano-engines of creation may go rogue and blanket the planet in a sea of grey goo. However, it is hard to imagine an artificial virus that couples a 100% infection and mortality rate, while subsequent research suggests that democidal nanomachine swarms will remain in the realm of science fiction. That said, there are many unforeseen pitfalls. Future technology is, almost by definition, unpredictable. So it is not impossible that even something that currently seems highly unlikely, for example particle accelerator experiments, if not a complete black swan, is what will do us in. Many experts believe that artificial general intelligence, AGI, will appear by the middle of the 21st century, 13,50-52. An artificial general intelligence, AGI, may be able to quickly bootstrap itself into a superintelligence, defined by Nick Bostrom as any intellect that greatly exceeds the cognitive performance of humans in virtually all domains of interest. Especially if this is a hard takeoff, the superintelligence will also likely become a singleton, an entity with global hegemony, and woe to us if it decides to convert us all into paperclips. Consequently, the control problem in AI is widely considered to be the most acute existential risk in futurist circles. It also happens to be largely irrelevant to this thesis, as it is one of the few existential risks that do not also constitute a great filter. Getting turned into paperclips will be bad for us, but irrelevant so far as the Fermi paradox is concerned. Functionally, all that will happen is that superintelligent machines replace humans as the primary agents of the Terran noosphere. Even if Skynet ends up killing us all, why would it stay on this planet indefinitely? More precisely, why would each one of the dozens to millions of past Skynets in our galaxy have uniformly decided to stay on their home planet, instead of beaming their presence out into space or physically expanding their dominion at close to the speed of light? Either machine superintelligence inevitably tends to suicide or stasis, which seems intuitively unlikely, though impossible to rigorously disprove since we cannot know the mind of a superintelligence before inventing one, or superintelligences have universally worked out that they shouldn't broadcast or expand into space from first principles. Assuming that we cannot dissolve the Fermi paradox to be sufficiently confident in our own solitude, and that geoplanetary and technogenic existential risks don't constitute credible great filters, what else could possibly explain the great silence all around us? Universe simulations. Anyone who believes exponential growth can go on forever in a finite world is either a madman or an economist. Kenneth Boulding. The concept of superpredator civilizations that winnow out any civilization that shows its head above the cosmic parapets, to remove potential competitors, for resources, out of pure psychopathy, is a popular sci-fi trope. Perhaps the reason everyone is silent is because killers stalk the star-strewn skies, hiding in the dark voids between worlds. I do not consider this to be a very plausible explanation, at least so far as the most commonly cited reasons are concerned. Since any such civilization will have many millions if not billions of years of technological advantage, a post-human space empire is unlikely to see any civilization at humanity's 21st century technological level as any sort of significant threat. Nor do I think it likely that they hunger for any resource specific to our humble clump of rock. The universe is full of rocks. Maybe they do it just for the hell of it, like the Reapers of the Mass Effect universe? Still, I don't think that's too likely. First, at least within the human species, empathy has tended to increase with literacy and social complexity, so it's not too obvious that an evil xenocidal race stalking the heavens would constitute the endpoint of sociocultural evolution. That said, as I will explain later, evolutionary dynamics may favor the emergence of such civilizations. Second, and more importantly, why would they snuff out fledgling space-traveling civilizations from the shadows, leaving open the chance that some particularly paranoid ones slip by their net, instead of openly exerting dominance and saturating the galaxy with their presence? Calculating space. But what if the resource in question is something a bit more esoteric? In a classic paper from 2003, Nick Bostrom argued that at least one of the following propositions is very likely true: that post-human civilizations don't tend to run ancestor simulations, that we are living in a simulation, or that we will go extinct before reaching a post-human stage. Let us denote these basement simulators as the architect, the constructor of the Matrix world simulation in the eponymous film. As Bostrom points out, it seems implausible, if not impossible, that there is a near-uniform tendency to avoid running ancestor simulations in the post-human era. There are unlikely to be serious hardware constraints on simulating human history up to the present day. Assuming the human brain can perform 10 operations per second, this translates to 10 operations per second to simulate today's population of 7.7 billion humans. It would also require 10 operations over the entirety of humanity's 100 billion lives to date. As we shall soon see, even the latter can be theoretically accomplished with a nano-based computer on Earth running exclusively off its solar irradiance within about 1 second. Sensory and tactical information is much less data-heavy, and is trivial to simulate in comparison to neuronal processes. The same applies for the environment, which can be procedurally generated upon observation as in many video games. In Greg Egan's Permutation City, a sci-fi exploration of simulations, they are designed to be computationally sparse and highly immersive. This makes intuitive sense. There is no need to model the complex thermodynamics of the Earth's interior in their entirety. Molecular and lower details need only be rendered on observation, and faraway stars and galaxies shouldn't require much more than a juiced-up version of the Universe Sandbox video game sim. Bostrom doesn't consider the costs of simulating the history of the biosphere. I am not sure that this is justified, since our biological and neurological makeup is itself a result of billions of years of natural selection. Nor is it likely to be a trivial endeavor, even relative to simulating all of human history. Even today, there are about as many ant neurons on this planet as there are human neurons, which suggests that they place a broadly similar load on the system. Consequently, rendering the biosphere may still require 1 or 2 more orders of magnitude of computing power than just all humans. Moreover, the human population and total number of human neurons was more than 3 orders of magnitude lower than today before the rise of agriculture, i.e. irrelevant next to the animal world for 99.9998% of the biosphere's history. Simulating the biosphere's evolution may have required as many as 10 operations. I am not sure whether 10 or 10 operations is the more important number so far as generating a credible and consistent Earth history is concerned. However, we may consider this general range to be a hard minimal figure on the amount of boring computation the simulators are willing to commit to in order in search for a potentially interesting results. Even simulating a biosphere history is eminently doable for an advanced civilization. A planet-scale computer based on already known nanotechnological designs and powered by a single-layer Matryoshka brain that cocoons the sun will generate 10 flops. Assuming the architect's universe operates within the same set of physical laws, there is enough energy and enough mass to compute such an Earth history within 10 seconds, and this is assuming they don't use more exotic computing technologies, for example based on plasma or quantum effects. Even simulating 10 billion such Earth histories will only take 3,000 years, a blink of an eye in cosmic terms. Incidentally, that also happens to be the number of Earth-sized planets orbiting in the habitable zones of Sun-like stars in the Milky Way. So far, so good, assuming that we're more or less in the ballpark on orders of magnitude. But what if we're not? Simulating the human brain may require as much 10 flops, depending on the required granularity, or even as many as 10 flops if quantum effects are important. This is still quite doable for a nano-based Matryoshka brain, though the simulation will approach the speed of our universe as soon as it has to simulate 10,000 civilizations of 100 billion humans. However, doing even a single human history now requires 10 operations, or 2 days of continuous Matryoshka brain computing, while doing a whole Earth biosphere history requires 10 operations, more than 30,000 years. This will still be feasible or even trivial in certain circumstances even in our universe. Seth Lloyd calculates a theoretical upper bound of 5 times 10 flops for a 1 kilogram computer. Converting the entirety of the Earth's mass into such a computer would yield 3 times 10 flops. That said, should we find that one needs significantly more orders of magnitude than 10 flops to simulate a human brain, we may start to slowly devalue the probability that we are living in a simulation. Conversely, if we are to find clues that simulating a biosphere is much easier than simulating a human noosphere, for instance, if the difficulty of simulating brains increases non-linearly with respect to their numbers of neurons, we may instead have to conclude that it is more likely that we live in a simulation. Computing costs of cosmic expansion. Let us for the time being assume that we need 10 flops to simulate a human brain. This would mean that we would need 10 flops to simulate the current world population of 7.7 billion, and perhaps 10-10 flops to simulate the entire biosphere. This is still many orders of magnitude higher than global computing capacity, which has been estimated to be around 2 times 10-1.5 times 10 as of the end of 2015, assuming median brain simulation requirements, 10 flops, and standard rates of growth in computer hardware, 25% per annum. These two lines shouldn't intersect until late in the 21st century. Under current computing paradigms, this suggests a near absolute guarantee of safety from simulation shutdown to around 2100. UN projections suggest that the world population will max out at 10 to 11 billion people by the end of the century. A 2004 meta-analysis of 94 historical estimates of the planet's carrying capacity, which at 7.8 billion is virtually equivalent to today's population. That said, another increase in order of magnitude during the following millennium cannot be excluded if proliferating pro-fertility genes were to reverse the demographic transition and bring the world to a state of Malthusian industrialism. Carrying capacity estimates specifically based on land/food as the limiting factor produced a much higher potential population of 33 to 103 billion, which also syncs with my own estimate of 100 billion as the planet's carrying capacity under current technological levels. Such a world will require almost 10 flops to simulate. However, these figures will rapidly inflate when we reach a post-human stage and start to radically expand our noosphere. This expansion can be either inward/microscopic, running more and more computations exploiting existing solar potential, outward/macroscopic, settling nearby star systems, galaxies, supercluster, or the entire universe, or both. Before we take a look at the computational requirements needed to simulate various expansion paths, it would behove us to first establish some basic numbers. As mentioned above, there are about 10 billion Earth-sized planets within the Goldilocks zone of Sun-like planets in our galaxy. There are also approximately 100 billion stars in our galaxy. Our local supercluster contains 50,000 galaxies. There are 100 billion galaxies in the universe. The Sun generates 3.86 times 10 joules, of which 1.74 times 10 joules reach Earth. For comparison, our entire civilization produces just 1.2 times 10 joules of energy per year. I don't bother accounting for wastage, since I assume that further technological development will assure that it doesn't translate into a decline of more than order of magnitude relative to 100% hypothetical 100% efficiency. There are currently 10 billion humans on the planet, and I posit that its carrying capacity with today's technological levels is 100 billion. Estimates for the human colonization potential of Earth-like planets is a factor of the number of stars and galaxies. I do not think there is much point in trying to estimate the human carrying capacity of like a ring world, i.e. in between an Earth-like planet and a Dyson sphere. If we are to expand to other stars and galaxies in a substantially non-biological form, for example, as 20-watt brains in a vat, as mind emulations, or as super-intelligent AI programs, then one may assume that all surface areas will be exploited to maximize the amount of energy tapped from the stars, up to and including the construction of Dyson spheres. Robin Hanson argues that sometime during this century, the new sphere will come to be dominated by silicon-based EMS, emulated minds. EMS reproduce by copying, and since copying has trivial costs, it can be expected that EM society will quickly reach its carrying capacity, depressing wages to subsistence levels. Since much of the brain's bit erasures are non-logical, Hanson suggests that EMS will be much more efficient than the 20-watt human brain and that the Earth will be able to support as many as 10 slow EMS. This presupposes decades worth more progress in increasing energy efficiency in computations, flops per watt, as well as orders of magnitude worth of optimization on brain models, i.e., removing non-logical computations. Regardless of how much effective computing power we manage to squeeze out of EMS, or AI software, the ultimate bound on our demand on the architect's computing resources is determined by energy and hardware considerations, to which we shall now turn. Table 2.2. Computing capacity, flops, needed to simulate various populations of humans, EMS, and superintelligences. One rather surprising consequence of the brain's computational efficiency is that a transition to a neo-Malthusian M or AI civilization running on nano-based hardware will increase the architect's load by no more than 7 orders of magnitude. Since 3 orders of magnitude and 10 orders of magnitude had already been spent on simulating all human history and the biosphere's history, respectively, remaining a Type I civilization on the Kardashev scale is unlikely to put the architect's supercomputer under undue strain. However, the equation changes rapidly once we start expanding beyond Earth and its measly share of the solar flux. Every major such expansion, harnessing the energy output of the Sun, Type II, the Galaxy, Type III, and the Universe, represents an increase of 10 orders of magnitude worth of computational potential. Even if expansion was limited to purely biological human colonization of Earth-like planets in the Milky Way, transforming them into 100 billion soul hive worlds like the Imperium of Man and the Warhammer 40k universe, it will require 10 flops to simulate. That's equivalent to simulating all human history every tenth of a second. Expanding to all potential Earths in the universe would require 10 flops. The fragility of biological life coupled with the vastness of interstellar distances means that cosmic expansion is likely to be dominated by silicon-based EMS or AIs. A typical scenario might involve a von Neumann probe landing on asteroids orbiting a far-off star, using the material to construct a Dyson sphere or Dyson swarm, and converting the structure into a Matryoshka brain. Based on perspective nanotechnologies, simulating just one such structure would require 10 flops. Converting an entire galaxy into Matryoshka brains would require 10 flops in computing capacity. That's the equivalent of 10 human histories every single second. It is also possible that post-humanity will invent computronium that transcends currently understood limits of engineering, so much so, perhaps, that inwards expansion will long remain more cost-effective than outwards expansion. In this scenario, it's feasible that it will eventually approach a one-to-one mapping with the architect's hardware assuming analogous laws of physics. Once we approach the architect's geographic extent, our simulation will take longer to run than the flow of time in the basement universe. The Cajon Hypothesis. Forget the power of technology and science, for so much has been forgotten, never to be relearned. Forget the promise of progress and understanding, for in the grim dark future there is only war. There is no peace amongst the stars, only an eternity of carnage and slaughter, and the laughter of thirsting gods. Warhammer 40k. If we are indeed in a simulation, there is a risk that the simulation will break down at some stage of these cosmic expansions, forcing the architect to Control-Alt-Delete us from our sector of spacetime. We have no obvious way to quantify at what point this will happen since we do not know how much computing power the architect have at their disposal, their future time orientation, the priority they allocate to ancestor simulations, or even whether their universe hews to the same physical laws as ours. As I have argued, the most that we can weakly posit is that the architect is sufficiently invested in us to have run the 10-10 operations needed to simulate the evolution of our civilization and/or biosphere, which might not have been especially interesting until recently. This establishes a lower bound for the sort of computing resources the architect has at his disposal. What effect could this be expected to have on the universe's geopolitics, its cosmopolitics? Rather paradoxically, the exact value of the simulating supercomputers or max value, its maximum achieved performance, may not matter nearly as much as the answers to the following questions. Do alien civilizations tend to believe that they are in a simulation? Or at least assign a non-trivial chance to the possibility? Once a spacefaring civilization spreads beyond the parent solar system, is there any chance of controlling further expansion? As I shall argue, a certain set of answers here will provide a crisp solution to the Fermi paradox. Do aliens believe in the Matrix? Obvious caveat that alien minds are alien. There are a number of good reasons why they might seriously consider the possibility that they're in a simulation. First, the capacity to imagine the world as illusion seems to have gone together with the evolution of a complex cognitive suite. It has appeared in various forms and throughout diverse cultures in world history, including primordial folk beliefs, the dreamtime of Aboriginal Australians, ancient philosophy, for example Neoplatonism, Zhuangzi's butterfly dream, esoteric interpretations of the major monotheistic faiths, Kabbalah Judaism, Gnostic Christianity, Sufi Islam, and heresies, for example Cathars, Bogomils. Of these, perhaps the most fascinating ancient example is Gnosticism, as it even anticipates the idea of a simulation within a mathematical structure. The existence of the demiurge, the creator of the material world, a premonition of the architect? Happens within the scope of the ultimate reality defined by monad, the one which is both bythos, deepest, and outside time, proarchy, which can be considered a metaphor for the abstract mathematical structures that define the metaverse. So it seems unlikely that intelligent alien beings would have difficulty with the concept. Second, metaphysics is becoming digital physics. Since the publication of Calculating Space by Konrad Zuse in 1969, the idea that computation is existence, that we live in a mathematical universe that can be crisply described as a set of mathematical relations, or that can be modeled as a cellular automaton or computer simulation, has become increasingly popular amongst physicists and philosophers. There is the practical observation that reality appears to be discrete at the lowest levels in both space and time, Planck units. The speed of light can be interpreted as the CPU's clock speed. The universe appears to be extremely fine-tuned in a way that is favorable to the emergence of complex life. Furthermore, a great deal of what Einstein called quantum spookiness, collapse of the wave function on observation, or future events determining the past, can be interpreted as the universe making liberal use of simplifying calculations. Just as with Schrödinger's cat, the typical RPG video game doesn't calculate the amount of gold in a treasure chest until you open/observe it. It would be surprising if aliens did not come up with broadly analogous digital physics interpretations of reality. Third, there may appear more telltale signs that we are living in a simulated universe. This could be in the form of what we might call lazy programming, such as the recent and unexpected discovery that all galaxies rotate at the same speed. Another, closely related set of possible evidence would be cosmic macrostructures that hint at an architect's involvement. One possible example is a supervoid at the CMB cold spot 6 to 10 billion light-years away. It is spherical in shape, 1,000 times larger than similar voids, and is supposed to be missing 10,000 galaxies. This translates into 10 flops to simulate that amount of hive worlds, and 10 flops to simulate that amount of Matryoshka brains, reminder that 10 operations are needed to simulate a biosphere history. Perhaps that region of space awoke several billions of years ago, spread in an expanding sphere, and had to be wiped by the architect? Moreover, perhaps the supervoid only became so big because it was the first to go into metastasis, and the architect could wait longer before shutting it down, since computationally intensive biospheres had yet to form in other parts of the universe? These are admittedly some crazy speculations. That said, it might be possible to devise more grounded tests in the future. For instance, philosopher Michael Johnson argues that apart from ancestor simulations, there could be two other good reasons to simulate a universe: 1, instrumentally, to calculate something; 2, intrinsically, to create a wide variety of interesting qualia. Finding that our universe is optimized for efficient computation, or that all our contingent physical variables are fine-tuned to create maximum positive valence, could potentially greatly increase our confidence in whether or not we reside in a simulation. Max Tegmark in the Mathematical Universe argues that we do not live in a simulation because of the problem of recursion. There is no apparent way to definitively establish you're not in the basement simulation, and because simulating a universe is much more computationally intensive than merely specifying the set of relations between its elements, which is all that his mathematical universe hypothesis requires. He argues that the existence of a memory stick within our universe containing such a set of relations would not increase the likelihood of finding ourselves in such a universe to any appreciable degree, considering that the multiverse is infinite in scope anyway. I do not really buy this logic, because even infinities obey the laws of probability. In any sufficiently large portion of spacetime defined by our universe's rules, the chances of us being in a simulation will converge to the quantity of simulated observer moments divided by the quantity of real observer moments. Obviously, we can only speculate about those ratios. However, as Bostrom himself points out, the mere fact of us starting up simulations, especially ancestor simulations, would massively raise the chances that we are within a simulation ourselves, at least so long as we can credibly recreate the observer moments we experience. That the ultimate reality, the one that the architect inhabits, may also be purely mathematical has no bearing on whether or not our reality is a simulation. The monad does not rule out a demiurge. The existence of operating systems does not make impossible virtual machines, nor does it even say anything about the relative ratio of total programs running between the two. Consequently, the fourth and last point is that if aliens manage to successfully run ancestor simulations, it will increase their confidence that they are themselves in a simulation. As already mentioned, they will have a variety of reasons to run such simulations. Critically, running simulations isn't likely to strain their own computing budget, at least so long as it remains fixed as a percentage of their total computing activity. The catch, of course, is that this may require repeated prunings of the simulation. Finally, it needs to be emphasized that there is no hard requirement that aliens believe or know that they are in a civilization for certain game-theoretic dynamics that will soon be expounded upon to come into play. It is merely sufficient that they either, 1. Assign a non-negligible probability to such a scenario, and or 2. Assign a high probability to other civilizations thinking in these terms, and assign a greater utility value to the survival and prosperity of their own civilization than to that of other civilizations. In both of these scenarios, even purely utilitarian considerations will dictate a certain set of cosmopolitical imperatives. Can expansion be controlled? The biological drive to expand, to exploit more ecological niches, seems to be innate to our species. This is also probably true for most intelligent alien species, since intellect evolves, in significant part, to the challenges of dealing with variegated environments. There is no reason to think space is an exception, as suggested by the sheer plethora of space opera-themed films, books, and video games. This sentiment was perhaps most succinctly expressed by Konstantin Tsiolkovsky, one of the founding fathers of rocketry. A planet is the cradle of the mind, but one cannot live in a cradle forever. Once a civilization sets up the requisite economies of scale, there are substantial material benefits to cosmic expansion. Even if increasing a civilization's power and prestige is too much of an anthropic motivation, there are no end of seemingly more universal benefits, such as increasing the energy/computing power at one's disposal, and providing redundancy against many forms of existential risk. This is one of Elon Musk's stated reasons for wanting to set up a Mars base. However, no post-human civilization, at least in the Milky Way, seems to have made a play for galactic domination. Moreover, we can be relatively sure that nobody in our neighborhood has gone much further than Type 2 on the Kardashev scale, i.e. fully harnessing the energy of its parent star. Nor is it immediately obvious why alien civilizations would hold back. After all, it's not like spreading to 2, 10, or even 100 new star systems will likely turn out to be the straw that breaks the horse's back, or short-circuits the architect's supercomputer. Increasing the computational load by many orders of magnitude, such as overspreading a supercluster with EMS? As we saw in Part 2, this is potentially much riskier. Settling just a few other worlds? Probably not. And the benefits to this are vast, since it would introduce a very substantial safety margin to a civilization's long-term prospects. But all this depends upon the critical assumption that expansion to other star systems can be indefinitely controlled. The reason is that while singletons, which can range from world dictators to global adherence to a set of ethical norms, are feasible on single planets, they become much more problematic to maintain across multiple planetary systems. The average distance between stars in our part of the Milky Way is around 5 light-years, which puts a massive lower bound on the speed of communications, not to mention physical contact, under currently understood laws of physics. Eventually, one world or another will start to ignore metropolitan edicts against further expansion. This will cause a snowballing effect, since the very fact of expansion will select for more adventurous, rebellious, fecund, and expansive cultures. Furthermore, having already defied the imperial center, this expansive culture will have strong incentives to rapidly maximize its power relative to the coalition that it is now sure to provoke against itself. This, perversely, will make it even more important for it to undertake further rapid expansion. Historically, one can make the comparison between China and Europe during the Age of Exploration. In the wake of Zheng He's treasure voyages from 1405 to 1433, the Chinese decided to scrap their navy to focus on the nomadic threat. As a centralized empire, it was able to institute progressive restrictions on private maritime trade, eventually limiting them to tributary missions. China was the dominant power in East Asia, both culturally and commercially. In neighboring polities, kings sought investiture from and kowtowed before the one emperor, the Son of Heaven. Consequently, the Chinese C-band, Haijin, was also adopted by its cultural vassals, such as Japan, Sakoku, and Korea. The term Hermit Kingdom predates North Korea. The Japanese policy, which lasted from 1633 to 1853, was even more draconian than China's, prescribing the death penalty for shipwrecked foreign sailors and Japanese who left the country and then returned, as well as their families and intercessors. Meanwhile, at the opposite end of Eurasia, there was no central authority that could mediate the intensely competitive and expansionist drives of the emerging European nation-states. Even the Pope's 1494 division of the world between Portuguese and Spanish spheres of influence was sooner a recognition of reality than its creation, and in any case it soon became entirely null and void as other European powers joined in the colonial rush. Moreover, it wasn't long before even the individual mother countries started to lose control over their settlers. The European colonization of North America became preordained as soon as their settlements became sustainable, despite subsequent efforts by the British to prevent American expansion over the Appalachians. And eventually, almost all of the settler colonies declared independence. Never mind 5 light years, even just exercising control over a 5,000 kilometers wide ocean proved too much for Britain, Spain, and Portugal. Furthermore, even controlling a human space civilization is likely to be much easier than policing EMS or AI superintelligences. Fundamentally, this is because the latter run on electronic circuits that switch 10 billion times faster than the 20 milliseconds that human brain neurons take to react. Robin Hanson projects that the typical M will run at 1,000 times human speed, while the very fastest cost-effective EMS will run at 1,000,000 times human speed. 1 second of thinking for the former will be half an hour for us, while 1 second of thinking for the latter will be more than 10 days for us. In a half hour that an ICBM takes to fly from the US to Russia, a very fast M can live out a typical human life. On a scale of light years, even Alpha Centauri, 4.4 light years, will be further away than the Andromeda Galaxy, 2.5 million light-year, so far as very fast M chronology is concerned. Since it is the fastest EMS that are expected to have the highest status and influence, this implies that interstellar communications will occur on an M-adjusted chronological scale that's longer than the existence of the human species. Now, assuming that EMS and/or AI superintelligence are possible in principle, it seems highly unlikely that any radical cosmic expansion will be based on a biological vector. Not for very long, at any rate. First, as already mentioned, the fragility of biological life forms makes prolonged space travel a much more physiologically and psychologically challenging ordeal than for their machine-based counterparts. Second, this probably wouldn't change even if a civilization makes a strategic decision, and has sufficient internal coordination, to ban the development of AI superintelligence, which it might do to reduce the computational load on the simulation, or because doing so would constitute an existential risk. For example, they work out that friendly AI is impossible in principle, or establish that EMS and AIs cannot have conscious experience. But will a state of Butlerian jihad last over the centuries and millennia, as the number of colonized star systems climbs from the dozens into the thousands and millions? As with the space colonization problem, there need only be one point of failure. Since EMS or AI superintelligences on self-replicating spacecraft may be expected to be much faster and more efficient space colonizers than biological ones cocooned within the generation or colony ships of classic sci-fi, they will rapidly overtake and outcompete the latter in the peopling of the cosmos. Moreover, while a transition to electronic-based space colonization may be merely very likely in the case of an initial biological expansion, this would rise to a near certainty if said initial biological expansion is unauthorized. After all, a planetary subculture that has scant regard for a civilization-wide prohibition on cosmic expansion is unlikely to take seriously taboos on creating machines in the likeness of a human mind either. In conclusion, it seems that expansion beyond the confines of one solar system vastly increases the chances of further expansion acquiring a metastatic or runaway character due to the practical difficulties of exercising control over distances measured in light years. Conversely, expansionist drives have a good chance of being contained on a single planet. There can be a global treaty mandating planetary isolationism. A sufficiently powerful coalition of countries can subject rogue polities that don't sign up to sabotage, sanctions, or military suppression. Counterintuitively, this problem may be even easier to solve on a single M or AI superintelligence planet. This is because any cosmic expansion will be effected through some kind of spaceship, but manufacturing, even at the nano level, would still be much slower relative to the speed of electronic thought than is conventional manufacturing relative to the speed of human thought. During the time it takes to construct a starship, faster EMS will get to experience the equivalent of thousands of years of human thought. During this period, EMS that support the isolationist consensus will have plenty of time to discover the project, if it is clandestine, to gather a coalition against it, and to sabotage it. That said, one may also think of counterarguments that suggest cosmic expansion will be harder on an M planet. Hansen posits that M society will be organized around clans consisting of multiple copies of the same basic model M. These clans will presumably have very high levels of internal solidarity and coordination. Should a sufficiently large clan take over a planetoid or large asteroid that's far from major M centers, one may posit that it will be able to construct starships and considerable security underground. Regardless of whether a human or M civilization can be expected to have a better handle on controlling cosmic expansion, these considerations strongly suggest a hard, natural limit to interstellar expansion under any circumstances, staying in one's own solar system. Space Sakoku and zero-sum cosmopolitics. Summing up, it is perfectly imaginable that advanced alien civilizations may adhere to the following set of beliefs. That they are in a simulation with limited computing power, or at least assign a non-trivial chance to the possibility. That interstellar expansion risks assuming runaway characteristics the more worlds it comes to encompass. That hypothetical alien civilizations come to hold similar beliefs. These beliefs may lead to a logically deduced and regionally evolved game theoretical equilibrium that keeps the density of computational activity in any given sector of space low enough that it doesn't overload the architect's mainframe. This equilibrium may be interpreted as the ultimate metaphysical Cajon, the biblical concept of that which withholds the coming of the end times in Christian eschatology, and has been variously associated with the Roman Empire, Christian monarchies, and the Hobbesian Leviathan. The Cajon may be expected to manifest itself in a set of behaviors that aims to minimize the probability of runaway cosmic expansion. What would be the components of such an equilibrium? Imagine we are non-player characters, NPCs, in the architect's video game. Through recursion, the architect fears that its own reality is also simulated, and at risk of getting shut down should they exceed the computing power assigned to their sector of space. After all, what would you do if an NPC in your video game was to start mining Bitcoin on your computer's GPU for their own benefit? Sooner or later, you'd probably Control-Alt-Delete them. Even more to the point, what would you do if you happened to be that NPC? First, you would refrain from spinning off more NPCs. This means no cosmic expansion, since child civilizations will compete for the architect's limited resources and increase the risk of ruin for everyone. They will live under the dictums of the heresiarch of Ukbar, a Borgesian character who proclaimed mirrors and copulation to be abominable, as they both multiplied the numbers of men. The solar system would be kept in a state of indefinite sakoku, with an absolute ban on spreading self-replicators, whether biological or machine, beyond it. Second, you would kill any other NPCs you come across. Shoot first and don't ask later. This consequence of zero-sum cosmopolitics may be termed mutually assured xenocide. It is essentially a modified version of superpredator theory, but with calculating space as the limited resource. Note that there doesn't have to be anything particularly pathological about it, and there might even be pangs of guilt and regret, though perhaps dulled by repetition and existential necessity, as our killers fire up the mirror beam at the epicenter of the radio emissions from our solar system, provided that they see us first. So it would really be regretful mutually assured xenocide, RMAX, with Solzhenitsyn's portrayal of life in the Gulag constituting the literary backdrop. May you die today, so that I may die tomorrow. But fire that mirror beam they will, because it is Remax that ensures the Remax delegated to our sector of space is not exceeded. Third, more speculatively, you would be incentivized to run ancestor simulations. As already mentioned, post-human civilizations may tend to do this for a variety of reasons, out of curiosity about their ancestors, to compute something, and or to investigate a broader range of possible mind states and qualia, psychonautics. Philosophically, they might also do it to increase their confidence that they are themselves within a simulation by fulfilling one of the conditions within Bostrom's simulation argument. If they are successful at this, this would make the Cajon hypothesis much more likely, and would also consequently serve a vital strategic role, such as analyzing how evolved civilizations react to the possibility of themselves being in a simulation, i.e. providing a sample of more than n=1, and the cosmopolitical implications thereof, i.e. would this lead to Remax dynamics? Ironically, this would also open up an additional incentive for alien civilizations to fire on sight, as a meta-strategy to reduce the risk that they are themselves within a simulation. The Remax equilibrium. Anticipating objections, I need to emphasize that the Cajon would be an evolved system. Areas of the universe in which it did not appear, or where Remax was not enforced rigorously enough, would have been wiped by the architect. On the other hand, the anthropic principle suggests that Remax was not so rigorously enforced as to have prevented the possibility of life developing on at least some habitable planets. Furthermore, an environment in Remax equilibrium can also be expected to select for a certain set of psychological traits amongst surviving alien civilizations. These are very likely to include paranoia, isolationism, and aggressiveness. The fundamental reason has to do with the observation that the offensive rules supreme in space. This is a function of the sheer destructiveness of hypothetical space-based weaponry, as well as the relative ease of stealth for civilizations that are so inclined. Trivially, one may launch dense pellets or objects at very high speeds, because energy imparted is a constant of mass but the square of speed, which furthermore becomes hyperbolic at relativistic speeds. However, aiming such a shot may be quite difficult from large distances. Alternatively, mega mirrors arranged around a star can generate a beam with the intensity of a 6750K blackbody, with a diameter equal to our Moon's orbit and a diffraction rate of only 50 km per 1,500 light-years. Such a beam would maintain the intensity of a star's surface, even thousands of light-years away. Even a temporary intersection with a planet such as Earth will fry its surface to a crisp. Another, admittedly harder, possibility is to fling large planets into the Sun. This isn't going into overly sci-fi weapons, such as nanomachines that can transmute a star's mass into elements that don't support fusion, as in Peter F. Hamilton's The Neutronium Alchemist, or exotic spacetime hijinks to speed up delivery times beyond light speed, for example Alcubierre drives or wormholes. They might be purely speculative today, but who knows what tomorrow will bring? Potentially, aliens can also send von Neumann probes programmed to kill, enslave, or otherwise constrain the cosmic expansive potential of native life forms. However, this may be risky, since any self-replicators still have the potential to evolve and go rogue themselves, nullifying the entire point of such a mission. Perhaps a safer and more productive use for von Neumann probes will be as spying/listening devices on lunar surfaces or asteroid belts, as in Bracewell's Central Hypothesis. It would be relatively cheap to seed most of the solar systems in a galaxy with such probes, especially those suspected of having habitable planets. In our own solar system, it might make sense to place them within the inner Oort cloud, which is far enough from the Earth, unlike the Kuiper belt, to avert detection for what is likely many more centuries to come, but not so far away as to have all radio emissions from Earth fade away into the background cosmic radiation. The low level of solar flux at those distances will deprive self-replicators of the energy surpluses needed for vigorous reproduction and potentially dangerous evolution, but might be just enough to allow them to effect self-repair and passive observation, and to communicate detection of artificially created radio waves to their masters. The one thing that all of these attack vectors have in common is that the victimized civilization would hardly have any time to know what hit them, let alone figure out where it came from. Even in the unlikely event that they regain their bearings, their own detection capabilities would have been massively degraded. Consequently, the civilization that launches the attack would have little fear of retaliation. Consequently, the correct game theoretical move under Remax equilibrium is to always defect. Cooperation only typically arises in repeated games, but the distances and scales of space warfare, plus the high risk of attempts at peaceful communication, since they are largely equivalent to dropping stealth, means that there'd be scant space for more positive dynamics to arise. Defection being the rational play would also subdue incentives to actively seek revenge, at least in the unlikely event that a civilization on the receiving end of a space bullet or mirror beam survives in some form. All this implies that the very nature of the Remax equilibrium would actively select for xenocidal aggressiveness. Just as any good or trusting creature dreamt up by mortals and given flesh in the northern chaos wastes of the world of Warhammer gets instantly killed by stronger and more evil entities, so too, perhaps, the less paranoid and aggressive space civilizations get snuffed out as soon as they make their existence known to the uncaring gods of the heavens. One team of futurists has argued that advanced alien civilizations estivate, quietly hoarding their energy surpluses so as to perform computations at a time far in the future when the cooling of the universe makes computing much more efficient. This would enable far more total operations, by a factor of 10, than if they were to start now. They calculate that a civilization burning through the baryonic mass of a supercluster can achieve as many as 10 operations. This should suffice to simulate an entire universe of Matryoshka brains for up to a sextillion years. That said, it should be noted that strong counterarguments have been raised against the estivation hypothesis. However, even if it is true, it would not constitute a refutation of the Cajon hypothesis. That is because even estivating civilizations will need to ensure that upstart civilizations don't emerge and smother them during their slumber, and/or metastasize and invite the architect's wrath upon their sector of space. Furthermore, The inventors of the estimation hypothesis make the exact same point, leaving autonomous systems to monitor the domain and preventing activities that decrease its value would be the rational choice. They would ensure that parts of the originating civilization do not start early, but also that invaders or young civilizations are stopped from value-decreasing activities. One plausible example would be banning the launch of self-replicating probes to do large-scale colonization. Consequently, they would, if anything, have even greater incentives to stymie foreign cosmic expansions than active alien civilizations. More speculatively, combining these considerations may suggest that an optimal strategy under the Cajon hypothesis may be to enclose a single star within a Matryoshka brain. The outer shell would constitute a clearly demarcated limit to cosmic expansion. It would give its owners extreme detection capabilities, massive telescopes, and offensive powers, space mirrors. It would also generate up to 10 flops worth of computing power based on theoretically feasible nano-based designs, which could be sufficient to simulate 1 million human histories within 1 second. Incidentally, it has been recently theorized that the KIC 8,462,852 star may be in the final stage of transitioning to a Type II civilization. It is 1,468 light-years away from us. If these speculations are correct, by far the strangest thing would be that they have reached a post-human stage just 2,000 years ahead of us. Set against cosmic timescales of billions of years, this would be a most amazing coincidence, unless, perhaps, the architects seeded every intelligent alien species at the same point in time in what ultimately translates into a gargantuan civilization video game. If so, this certainly doesn't bode well for us. We'd have come to a tank battle armed with spears. Navigating the black seas of infinity. We have been blithely broadcasting our presence to the dark void above for more than a century. Even if commercial radio or TV broadcasting is too underpowered, the radar signals from Russian and American ballistic missile early warning systems should be detectable from any part of the inner Oort cloud that happens to host an alien listening post with the detection capabilities of the Arecibo Observatory. If the Cajon hypothesis is true, then our doom may already be written onto the stars. Still, it's not yet too late to take some proactive measures to give us at least some chance of survival if worst comes to worst. 1. We need more research. This sounds banal, but it's true nonetheless. We need to think more about how to prove, or disprove, the Cajon hypothesis and accurately identify the Remax equilibrium's position within the hierarchy of existential risks. In particular, we need to do more of the following. Generate much more precise estimates of the likelihood of potential great filters in the past. This should be done anyway, since narrowing down the past parameters of the Drake equation is also critical to clarifying just how much we should be worried about existential risks in principle. Continue researching and working to mitigate technogenic existential risks. Continue searching for more evidence on whether our universe is a simulation or not. Continue working on simulating more complex neuronal structures, to establish the computational cost of simulating minds of varying complexity, and how granular the simulation needs to be to accurately simulate their behavior. Explore the nature of qualia, of consciousness, and of whether they can be rigorously measured and simulated. The answers to these research questions will determine the attention we will need to pay to subsequent recommendations. Depending on the results of these investigations, it may still be worthwhile trying to enact some form of emissions control, even though there's a good chance it will be politically impossible, and far too late anyway. In a personal communication, Michael Johnson suggests that we also need to explore what sort of predictions the Cajon hypothesis implies. For instance, are there cosmological predictions that would add to our confidence about the Cajon hypothesis if they were later discovered to be true? Possibly the two most likely places to look are cosmological observations and contingent variables in the Standard Model. Does the Cajon hypothesis make any cosmological predictions, or predictions about what the apparently contingent but apparently fine-tuned variables in the Standard Model might be exactly optimized for? 2. Absolutely no active SETI. One doesn't even need the Cajon hypothesis to see why this might be a bad idea. 3. We may consider instituting radio emissions control. This will be politically tricky, though possible for a determined singleton. The main problem is that it's probably far too late for that. Nonetheless, it may still be worthwhile if the deduced likelihood of Remax equilibrium is sufficiently and alarmingly high. 4. We need to get good at identifying small objects in space. If our sector of space is in Remax equilibrium, alien civilizations are likely to have seeded space with secret listening outposts trained to recognize the appearance of intelligent civilizations within their sectors, and relay their findings for all the universe to hear. There's no particular reason that the spotter and the sniper have to be the same civilization. we will need to comb nearby planetary and asteroid surfaces. As mentioned, there is a good chance that any such sentinels will be located in the Oort cloud, exploring which is beyond our present capabilities. However, doing this for nearby planets, moons, co-orbiting objects, and the Kuiper belt is already on the cusp of technological feasibility. 5. There must be hard restrictions on interstellar expansion until we can disprove the Cajon hypothesis. Even if there are no hostile aliens, such an expansion is likely to eventually assume runaway characteristics and doom us to eventual simulation shutdown. 6. Nonetheless, we need to recognize space technologies as important complements to reducing existential risks. Dispersing our civilization over the solar system would increase the chance that at least some humans would survive the Earth getting fried by a directed energy weapon or hammered by a hypervelocity projectile. Especially prospective avenues might include early warning systems for incoming projectiles, black holes, mirror beams, if our orbital path is targeted, etc. Nuclear pulse propulsion, or ion drives, by far the most cost-effective way to quickly get huge masses of matter out into space. Colonization of Mars, Venus, and some lunar bodies, with the ultimate aim of making them self-sustaining. Although as we have seen there is a strong case for banning cosmic expansion, it may nonetheless be useful to have related technologies on the drawing board should our own planet or solar system come under imminent risk of extermination. This would include life support, life extension, and/or cryopreservation technologies to enable interstellar travel. However, even if we manage to navigate to a habitable planet in another solar system, we will still face the renewed challenge of radio emissions control. This would require research into social technologies or structures that can maintain ideological consistency over the long term. Alternatively, it may be worthwhile locating geothermally active rogue or Steppenwolf planets and brainstorming ways of colonizing them. Their location in deep space and lack of a gravitational tether to a star makes them much harder to locate and track, and an underground civilization will have fewer opportunities or need to blast out its presence to the heavens. 7. We need to be careful about transitioning to a post-biological form of existence. The pros and cons need to be carefully weighed. It is possible that controlling cosmic expansion will be easier for EMS or AI superintelligences. On the other hand, merging with the machine would very likely increase the computing load on the architect's supercomputer by several orders of magnitude. 8. If you gaze long into an abyss, the abyss also gazes into you. Should we reach the post-human stage, we may need to develop our own Remax enforcement tools, even if it doesn't currently exist within our sector of space. If we conclude with high confidence that the calculating space we inhabit is strongly limited, it would be incumbent upon us to stymie the cosmic expansions of emergent alien civilizations in the future. It is not too early to start thinking about how we might do that as reliably and humanely as possible.